So number one, the chlorine smell of pool water is not in fact due to chlorine. When chlorine hits water, some of it reacts with the water in the following way. 2Cl2 plus 2H2O equals 4HCl plus O2. The smell of the chlorinated pool is often the smell of the HCl produced in this reaction. What is the delta H? And we're supposed to use bond energies. In order to solve this, we have to use Lewis structures. So remember, we've got to draw our the pictures of each of these molecules. All right, so Cl looks like this, Cl with our two extra dots here, and it has one bond. You can look that up on your periodic table. There's two of them, so we're going to put Cl, Cl. Our H2Os, we know, kind of looks like this. Our HCl is Cl to H, and we've got four of those, and our O's is just O to O, single bond. So when we look that up, 2 moles, and this is kilojoules per mole, and we're going to get rid of that. So we're not going to keep writing that, but just so that you know that's what we're doing. In this case, we're just going to add and subtract just as it's written. So 4 times 459 minus, because this here's our minus right here, minus 4 times 428 minus 494, because the in our chart the O to O bond it takes to break it. So we're looking at the formation and breaking of all of that. When we add all these together, we get our delta H equals a plus 110 kilojoules. Okay, number 2, benzene, C6H6, is a toxic liquid with a delta H at formation of 49 kilojoules per mole. The best method for disposing of benzene is to burn it in the presence of excess oxygen. What is the delta H for this reaction? All phases are gases except for benzene, so use Hess's law. All right, since we know it's a combustion or there's burning involved, we have to add our excess oxygen. We get CO2 plus H2O. So we've got to now see if we can balance the equation. Currently we have C6H6, O is 2. Over here we have C is 1, H is 2, O is 2 here, plus 1. Now, if we've got O2 over here, we've got to get this into a even number. We have H6 here, so if we do 3 here, this makes this odd, even though it fixes this. So we're going to have to make this 6. So that will make this into a 6. That makes this into a 12. We have to then put a 2 here to make this into a 12. That makes this also makes C also a 12. So we've got to come back here and fix this one, which makes the C a 12. And now this makes it a 12. So we've got everything but the O2. So 12 plus 6 is 18. That makes this 9. Oh no, we know delta H of formation is 49.0 kilojoules per mole. And we want the delta H of this reaction. So we were actually looking for the delta H of this. Delta H equals the sum of the delta H of the products minus the sum of the delta H of the reactants. We're going to move it here and here, minus here and here. Okay? So we have 12, we'll start off with this guy, 12. CO2, when you look that up, you get minus 394. We're adding that with the 6 of the H2O, and that's minus 242. Now we're going to start subtracting, and for the C6H6, there is 2 of them, and we know what that is because of this. They told us that 49, and it's a positive. And then our O2, which is coming here, it's 0. So it doesn't, there's no formation. When we add all that up, we get delta H equals minus 6278 kilojoules. And that's our answer. We're on problem number 3. When coal is burned in a power plant, it usually contains a small amount of sulfur contamination. The sulfur burns along with the coal to make SO2. This sulfur dioxide then begins to travel up the smokestack where it reacts with oxygen as followed. 2 SO2, which is a gas, plus O2, which is a gas, makes 2 SO3. If the delta H of this reaction is minus 198 kilojoules, what's the delta H of SO2 as a gas? Our reaction here, we know our delta H of the reaction is this, so I went ahead and put it there, but we're going to need it in this form. We're looking for our delta H, and we've got our formula here, which is Hess's law. So now we're just going to start plugging and chugging to see where we get. We know that our delta H, we have the delta H of the reaction, minus 198 kilojoules, equals the delta H of the products. So we're going to figure what that is. Remember, we have to go this way, this way, this way, minus, right? So 2 SO3 is, so what we have is 2 times a negative 396, and that's our moles and kilojoules over moles, but we end up with just kilojoules. Subtracting, remember, our O2 doesn't count because it doesn't have a formation. And then we have 2 times what? So we're going to have to figure 2 times what for this. All right. Now we can just start to plug and chug, really. We're going to just do the math. This equals minus 792 kilojoules minus 2x. All right. And we can mathematically just move this right over. So we have minus 198 now plus 792 equals a negative 2x. That would equal 594 kilojoules equals minus 2x. And we take this negative 2, bring it over, and divide it because we have to isolate for x, remember? So I'm going to flip this. It's easier for me. Equals minus 594 over 2, and that gives us x is minus 297 kilojoules. Our delta H of SO2 equals minus 297 kilojoules. All right, number 4. Using the delta H you got in problem 2, calculate the number of kilojoules of energy released when 250 grams of benzene are burned in excess oxygen. Here's our balanced equation. 2C6H6 plus 15O2 makes 12 CO2 plus 6 H2O with the added energy of 6278 kilojoules. So it's exothermic, so it ends up on this side. Now we have 250 grams of the benzene, so the question is how much energy is released. So we're going to have to use this as a ratio. We have to find our AMU, which we did here, and it's C6H6. Our AMU is 78.1, which is also 78.1 grams in 1 mole. So we don't have 78.1 grams, we have 250 grams. So we're going to go ahead and find our moles. 250 grams C6H6, that's in our sample. We multiply our grams, so we have 78.1 grams in 1 mole. And we get 3.2 moles of C6H6. All right, so we have that. Now we have to find out how much energy is released, and that's not super hard to find because we'll use this and this to help us find how much energy was released. So if we have 3.2, because remember we have to, in stoichiometry, we have to make everything go to moles before we compare them. That's in our sample. That's a 3.82. And we're going to compare it to our energy. For every 2 moles, we get 6.278 kilojoules. And we multiply that out, we get 10048 kilojoules. But because of this number here, we have to put it in sig figs. And that's your answer. All right, so number 5. Suppose you synthesize ammonia with the following reaction. 2NO2, which is a gas, 7H2, which is a gas, makes 2NH3, which is a gas, plus 4H2O. How much energy will be released if 70 grams of NH3 are formed? So here's our balanced equation. This is what we're looking for, which is the delta H of the ammonia. And we are looking for how much energy if we make 70 grams. So first we have to find our delta H. And so according to our Hess's law, delta H equals the sum of the delta H of the products minus the sum of the delta H of the reactants. So if we put our products over here and our reactants over here, and actually this would go, our reactants have ended up there, right? So here's one product, here's another product, and then our reactant is there. And if we do that, add them all together, you can see I had 4 moles. And for the first one, which is over here, kilojoules minus 242 kilojoules over moles. And I can get rid of the moles, so I'm just going to keep it that way so it's easier to read. I get minus 1126.6 kilojoules. That's my total delta H. So I'm going to go up here and put plus, let's see if I can do it right, plus 11. And I think I'll just do 27 kilojoules, right? So that way we know that we are going to deal with this later. All right, so then obviously we have to do our AMU because we have to convert from 70 grams into moles in order to make this comparison. I find out that 70, so NH3, there's 17 grams in 1 mole. So now I can convert my 70 grams. So 70.0 grams of NH3, that's in our sample, and we have 17.0 grams in 1 mole. And when we divide that out, we actually get 4.12 moles of NH3. So now we can use our comparison of this to this and find out how much energy was released. So we take 4.12 moles. That's our sample. This should be familiar to you because we've done this 100,000 times, except we're now converting to energy. So for every 2 moles, that goes on the bottom because we're converting out of it. We get 1127 of kilojoules. Our moles go away, and we get 2,320 kilojoules. And they said 2.3 times 10 to the 3. All right, so we're going to go ahead and do 6. What is the sign of delta S for the following reactions? Remember, we're looking for entropy, so we want to see, we're trying to find chaos. And so we are looking for the most chaotic thing. Gas is the highest, liquid or aqueous is next, and then solids are the least chaotic. And that makes sense, right? So We're looking for if we can find gas in any of these equations. Here's one here on the reactant side, and there are no gas molecules on the product side. The sign is negative. So the reactants have the higher entropy. On B, we're looking at, on the reactant side, we have a solid and a liquid. And on the product side, we have a gas and a gas. So that's obvious. The products have the most entropy, and that would make it a positive. All right, and on C, we have a gas and gas and gas and gas. Oh, wow. Okay, so now we have to look at the stoichiometric coefficients. So we have 1 and 1 because there's no stoichiometric coefficient, so we know that they just represent 1. So there's 2 molecules on the reactant side, and then 1, 2, 3, 4. So 4 on products, and since the product, if it's on the product side, it's a positive, that makes this a positive as well. All right, we're on number 7. What is the delta S of the following reaction? H2O, which is a liquid, plus CaO, which is a solid, makes CaOH2, which is a solid. Here's our reaction here. And we know that our delta S equals the sum of delta S products minus the sum of delta S reactants. I went ahead and put those down so it'd be easier. Remember that we're looking at the stoichiometric coefficients to help get rid of the moles. So in this case, it's 1. There's only 1 mole of this, or 1 item. So we're going to put 1 mole times 76.1 joules over moles times Kelvin. That means we can get rid of the moles. So I went ahead and did that already for these two. So our H2O is here, and our CaO is really here. And we're subtracting both of those. So our delta S becomes minus 32.0 joules over Kelvin. And that's it. Now remember, you had to use a different chart for this, so you had to keep track of your charts. All right, for number 8, if the delta H of a certain reaction is minus 1023 kilojoules per mole and the delta S is minus 324 joules over moles times Kelvin, what is the temperature range for which this reaction is spontaneous? Here we've got our delta H, which is 1023 kilojoules per mole. We have our delta S. Those are the things we know. We're looking for our temperature range to be spontaneous. And we know something about being spontaneous. It has to be, the delta G has to be less than 0. But in this case, in order to solve our problem, we're going to make delta G 0. All right, so now we have delta H minus T times delta S. And we are in fact going to isolate for T because that's what they're asking us for. So we're going to start by moving this over. We have minus delta H equals minus T times delta S. Now we're going to move that delta S over. So we have minus delta H over delta S equals T, minus T. Now, the nice thing about those minuses, that this minus and this minus will cancel each other out, so we don't have to worry about that. So here's the formula we're going to work with. T equals delta H over delta S. Do we have that? Absolutely. Look at this. We've already got that. T equals delta H, which is minus 1023 kilojoules per mole. Can we put our delta S down here? No, because our joules do not match our kilojoules. So we have to fix that and convert that joules to kilojoules. And simply to do that, we just have to 1, 2, 3, count to 3 and put our decimal here. So we can have negative 0.324 kilojoules over moles times Kelvin. So that's going to be the number we work with. So we're going to put negative 0.324 kilojoules over moles times Kelvin. That gets rid of our moles and our kilojoules, which is great because we need our temperature to work out. Our negatives cancel each other out. So we get 3,157 K. Now that makes delta G 0, right? So that's this temperature has delta G as 0. But since delta G has to be a negative, so we have to, delta G actually has to be a negative. That's what, in order for this to be spontaneous, then we know that we can't get up to this number, otherwise we reach 0, and that's not a negative. So the range of T is has to be less than, so T must be less than 3,157 K. They said T is less than 3.16 times 10 to the 10 to the 3K. But that's, either of those are right. Okay, for number 9, determine the activation energy and delta H for the following reaction. So we know that we've got where the reaction starts and where it ends. We also know that delta H is H final minus H initial, right? So our delta H is, the final is about 190 kilojoules minus, and it starts at 1200. So 190 minus 1200, our delta H is minus 1010 kilojoules. They said 1000. So either one is right. All right, activation energy is where the reaction starts and at what temperature does the reaction actually occur. So what before the reaction, and then what it takes to get the reaction started. So we're looking for the difference between the top of the hump to where the reaction started. And it looks like it starts at 1500. We subtract 1200, and these are all kilojoules, equals 300 kilojoules. So our activation energy is 300 kilojoules. All right, is this reaction endothermic or exothermic? The delta H is negative. So therefore, because it's a negative, it's exothermic. All right, for number 10, is the following reaction spontaneous at 298 Kelvin? 2 C6H6, which is liquid, plus 12 H2 gas, plus 3 O2 gas makes 6 C2H6O, which is, so we have our reaction written out. The question is, it spontaneous at 298 K? We need to remember that in order for something to be spontaneous, delta G has to be less than 0. So we're basically going to find delta G. We know our formula, delta G equals the sum of delta G formation products minus the sum of delta G formation reactants. Since our H2 and O2 were already formed, there's no energy to count for those, so we got rid of them, and our products go in front, and we subtract the reactants. So we have 6 times negative 175 minus 2 times 125. Our delta G will equal minus, that's a bad 6, minus 1300 kilojoules. And because delta G is a minus, the answer is yes, it's spontaneous. And that's all we needed to know.